instead of just having fuses, which is something that we have been doing. Excuse me. Okay. Which is something that we have been doing for forever, using fuses. Now we have more advanced devices to protect the grid. Reclosers, we have trip savers. Now we have this product, vacuum fuse. So we are kind of phasing out technologies that are that have served well the grid, but are not as intelligent as modern technologies. And this is an example of what I was mentioning before. This is what Hawaiian Electric, the utility that provides service to Hawaii, which has one of the highest penetration levels of solar generation in the world. This is the type of technology that they are deploying in their grid. So the vision is, again, to be able to operate the grid in real time, to have a state estimator like we do in transmission, eventually to have even microgrids deployed all over the distribution grid, and those microgrids helping us improve, again, resilience and reliability performance. If we want to do all of this, well, we'll have plenty of data. And in many cases, we need to process and analyze that data to be able to implement solutions. So analytics is going to be very important. It's already very important, but the thing that is really interesting is that, let's see, traditionally, when we say analytics, we tend to focus on the past, on analyzing the past and the present. But more and more analytics are getting into analyzing the future, trying to predict what may happen, and then based on those predictions, prepare the grid to prepare the grid so performance is not impacted when those conditions happen. So that is where we are. I would say where we are heading now, and there are solutions that use data, high resolution data, to try to predict, for instance, equipment failure, and or to try to predict, let's see, try to forecast loads and try to forecast DER output and try to forecast electric vehicle charging patterns, etc. AMI, well, AMI is foundational also to the distribution grid. Any modern distribution grid must have AMI, smart meters that allow us to understand consumption better at end user level. But AMI is much more than just meter reading and billing. You can use that data for so many things, and here we just describe a few of them. I mentioned asset monitoring and diagnostics. That's one of them. One of the things that you can do, plus managing DER, improving outage management, and others. So that's another key component. And electrification is certainly another important element of grid modernization, and it's important because when electrification happens, depending on where it happens, but if it happens, for instance, if a big company like Amazon or Pepsi or FedEx decides to electrify its entire fleet of vehicles, then we're talking about hundreds or thousands of vehicles, and some of those vehicles may be clustered in locations in campuses, for instance. And they may charge at the same time. So we are talking about, in some cases, of hundreds or dozens of megawatts that need to be added, capacity that needs to be added to the grid in a matter of, in some cases, months. Because electrifying a fleet is on the user side of things. Once the decision is made, is not that time consuming, but then the grid becomes a bottleneck. Upgrading the grid becomes a bottleneck because we have lead times that prevent us from building a new substation in a matter of months, right? We need to buy land in some cases. We need to complete environmental studies, permitting, etc., a variety of things. And so building a substation may take years. So those are new challenges that that we need to figure out, that we need to address. But electrification is a very important aspect of grid modernization. So I mentioned, okay, we need to forecast load, we need to forecast DER, etc. So in general, we need to update the way we plan the grid. And this talks about that to some extent. I think that what is important to emphasize here is that there are two aspects to planning the grid: the temporal aspect, time related, and then the spatial aspect, which is more geographical, the geographic component of planning. So in the past, it was enough for to plan the distribution grid to focus on substations and the beginning of feeders, and to focus on annual peaks. So it was relatively simple. With all of the things that are happening, with how dynamic the grid is now, then we need to have more resolution on the temporal side of things. The annual peaks are not enough. Depending on the type of asset, depending on the location of DER, electrification, etc., patterns as well, consumption and production patterns, peaks may not happen at the same time or around the same time of the year. For instance, summer peaks here in the U.S. usually happen around August or July in utilities. But again, depending on all of the factors that I mentioned before, some feeders may experience peaks in some sections of the feeder in other months. So what we are trying to do now as an industry is to do an hourly analysis of the grid, and in some cases sub-hourly analysis of the grid. So you may have heard about 8760 analysis, which is 8,760 hours of the year, basically understand performance and to plan the grid on an hourly basis. So that's the temporal component. And then the spatial component is more related with geographic resolution. So I mentioned feeder sections, right, rather than just feeder head and substation. So now we're moving into trying to understand and trying to plan even at service transformer level. So that's the approach that we are heading in that direction. Another element that is important is that in the past, the planning, transmission, and distribution systems was something that used to be done. And there was some coordination. Still today, there is some coordination, but it's largely two separate activities. There is some data and information exchange, but it is not done jointly. But we, as an industry, have realized that joint P&D planning and generation as well, resources in general, makes sense, because investments that are being made in distribution, I'll give you an example, being able to control loads in distribution, being able to have a flexible power production and consumption profile in distribution is something that can be used by transmission to address needs, like capacity needs would be one of them. So it makes a lot of sense to plan the grid jointly, and that is a big industry trend. So this is just an example of that trend, integrated distribution planning or integrated generation, transmission, and distribution planning. Besides that, we know that now DERs are here to stay. We know that the future of the grid will consist of hundreds of thousands of distributed resources. Now that we know that, we need to make sure that that grid of the future is DER ready. What we have been doing in the last 10, 15 years is basically upgrading the grid on an as-needed basis when we interconnect DER and we realize that DER interconnection is impacting the grid. So we are being reactive. So the paradigm shift now is to be proactive. We know that they will come, so what do we have to do so they can be interconnected in a seamlessly manner? What can we do to be ready? And we need to look at all of these different areas. So that's another component that is important for grid modernization. This is just an example of why it is important and why it is so challenging to plan, to design a distribution grid with DER because of the variability of DER production. And this is an example. This is real data from a power plant, a PE plant in Tennessee here in the US. And you can see there are beautiful days where the production is as it is supposed to be, a smooth curve. There are days in which there is plenty of variability. There are days where there is basically no production. There is overcast. So it's really challenging to plan a system that is flexible enough to accommodate all of this. Okay, so this is another example. This is real data. Another challenge that we are experiencing as an industry is the fact that now distribution systems are becoming active systems. So they are injecting power into the transmission grid. In the past, distribution systems only consumed power. Now they are starting to inject power into transmission. So that's why, again, it makes a lot of sense to plan both systems together. But variability is a big challenge. You can look at this you can look at it in this slide. This area in pink is an area where the system, the distribution, this distribution substation is injecting power to a transmission or subtransmission system. The area in white is an area where the transmission system is delivering power to the distribution grid. So you can see that in a matter of minutes, there is a transition between those two operating modes. So we need to be prepared for this. So this means that we need investments in equipment. Equipment needs to be ready to operate with this type of variability. So initially, our main focus in the industry was to understand very reactively what may happen and then address these issues in a reactive way, especially for large plants, large DER. And after that, we started experiencing more and more adoption at residential level. And when that happened, well, there was a clear need for new planning solutions. And when a DER adoption at residential level, there are impacts as well. So this is just one example from a real system. This is a service transformer. Here in the US, we use single-phase service transformer, popular. So this is just an example of a load profile on a service transformer in an area that is, again, where there is reverse power flow. Basically, the service transformer is injecting power into the distribution grid. And you can see that happens basically every day. There is some variability as well. But when that happens, then voltages, respective voltages at that service transformer tend to increase, and there are voltage violations that need to be addressed now. So again, very challenging situation. You can see that voltage increase is perfectly correlated with reverse power flow or power flow injection from distribution from low voltage to medium voltage level. Let me skip this. More and more in the long term, and that's where we are right now, the focus is not only the technology and infrastructure aspects, but also businesses, business processes, information systems, especially how is this going to affect the way utilities operate, and how is it going to affect also rates and other topics. So that's where we are focusing on right now. Excuse me, let me. I'll skip this one. This is just the next ones are just basically examples of some of the leading industry practices around each one of these topics. All of these topics are relevant, are components, programs of grid modernization roadmaps. This is just examples of specific utilities that are considered the leaders in each one of these areas. One of those interesting areas is what we call hosting capacity. Is basically analyzing the grid to understand the amount of DER that can be interconnected to the distribution grid, and then use that as a guideline for developers and for customers to interconnect their systems. So basically, in this specific case, these areas in red are areas of a distribution system where there is barely enough capacity in the grid to interconnect distributed resources without causing impacts. So as a developer, I'd rather not go and try to interconnect systems to those areas, because very likely it's going to trigger an improvement project, and then developers will have to pay for it. Instead, it's better to go to areas in green or orange, etc. So that's just one example. It's something that utilities are developing and publishing to assist customers and developers. Another one is, I mentioned before, monitoring the grid with higher resolution and using that data to evaluate performance. Synchronized measurement technologies is one example. This is something that we developed recently for the North American Synchrophaser Initiative and the U.S. Department of Energy. It's a roadmap that identified applications of synchronized measurement technologies in distribution systems to improve monitoring and system analysis at distribution system level. So one example of some of the things that the industry is doing, I mentioned the deployment of distribution class 5 devices, the deployment of microgrids, the deployment of energy storage. All of those are grid modernization initiatives that are very relevant for utilities. The deployment of automation systems and understanding better the relationship between automation and protection and control, and also reliability and resilience, and use that relationship to plan the system better and to justify this investment better. Let me skip this one. I'll skip this one as well. These are just examples of how using automation you can improve reliability, you can improve resilience, and the importance of when deploying that type of technology to look at those areas, automation, to look at protection, to look at control, and to look at benefits holistically. Let me skip all of this. This is the last two slides. Just to summarize, I think that this is a very exciting area, and I'll share the slides with you. There are so many different topics here that are important, that in which we need, especially I would say, young engineers to continue contributing, right? To lead the industry. We are going to pass the baton to you guys to some of these solutions and to implement some of these solutions. So I would encourage you all to continue learning about this topic, to find an area that you like within grid modernization, and to explore it, in detail. This is a still ongoing work, and there is plenty of work to do. So we are just beginning, and I would say we're still scratching the surface of what needs to be done. So when we start with grid modernization, I mentioned developing a roadmap is the starting point. And when you develop that roadmap, basically you identify the components or the programs that are involved in modernizing the grid. You justify them by calculating benefits and costs. You prioritize them, and then you develop a schedule for implementation. So that's the starting point. To do that, certainly you need to consider key drivers. DER integration is one of them. You also need to think about more and more, because of DER adoption, you need to think about more and more as a power delivery system, rather a joint power delivery system, rather than just as transmission or distribution. That separate view that we had in the past is not useful anymore. We need to look at it as power delivery T&D together, and also, of course, consider the production side of things, both generation as well as distributed energy resources. And we have all of these investments that we need to make on telecom, on IT systems, on analytics, artificial intelligence, all of that. That's also very, very important. And modeling the grid in more detail and automating simulations and conducting more detailed simulations with the data that we are going to have once we deploy sensors, once we deploy AMI, etc. That's also very, very important. This is the last slide. These are some of my publications and publications I have made with colleagues. They describe some of these topics in more detail, so I would encourage you to take a look at them, and if you have any questions, please email me. I'll be happy to reply your emails. And I think that now we have about 10 minutes for Q&A, so I'm happy to answer questions this afternoon, UK time.
Thank you very much, Dr. Julio, for your presentation. That was very, very educative and concise. It's question and answer session. I think I've been seeing some questions here. Let me just go through the chat section. Can you connect behavior of clients and performance of the network? Sorry, Gomez, if you're online, can you switch on your mic so you could ask your question directly? I think it would be very good.
Yes, please. Yes, please. Thank you very much for this conference. It was a very nice conference. I have a question. I was working with a company in Colombia, in Latin America, that has troubles because we need to upgrade the system, but we don't have enough money. And I am wondering three questions: how to renew the equipment to make them available to data? How can we protect the equipment from damage when the behavior of the client change? And what is the relation between the behavior of the client and the operation of the system?
Let's see if I understand correctly. So to protect equipment when customer behavior changes?
Yes.
Was that your question?
Yes.
And by protect equipment, do you mean, for instance, against overloads or high voltages and things of that sort?
Yes. But remember that you have the same problem. The damage can be inside the house or the building of the client, but also it can affect the network, because if you are producing energy because you have a photovoltaic system, you can damage the transformer. How to protect them and how to address that complexity in the new networks that we are using right now?
Sure. So you may remember that in this slide, I mentioned that standards, right? Standards is a component of grid modernization. It's a very important component. And there is more work that needs to be done in this area, but addressing your question specifically, one example of how you prevent some of those things from happening is to develop interconnection standards, or DER, right? So all utilities have an interconnection standard, and sometimes it's either utility specific or it can be jurisdiction specific. It may be a country, an entire country. So all utilities operating in that country follow that interconnection standard, or it can be a province or a state or a departamento. That could be an example, right? It may be applicable to a geographic region within a country. So that's one example. And another one is the more technical standards like IEEE 1547, which is a standard that governs the adoption of DER in distribution grids. So those are examples, and you need to develop standards and then, of course, enforce them. You need to make them available to the public, and public needs to comply with it. So that's one example. Now, another one is system analysis, and that's why models is also very important. So if you want to understand potential performance, future performance, well, you need to model the grid in detail, and you need to conduct simulations, and you need to understand what may happen to the grid. And then if you identify potential problems, then you need to address those problems in advance rather than reacting. So those are examples of some of the things that that you need to do, and addressing those problems proactively could be, well, I need to replace a transformer, or I need to replace a switchgear with something that is more suitable for operation with DER, or for operation with electric vehicles. Does that answer your question?
Thank you so much. Very interesting question. Answer.
Thank you so much. I've got a question here. Dr. Julio, you talked about the opportunities, advantages, and the modifications that will have to be made on the grid in powering a very sustainable future. And one of the high points was data analytics. And when you mention data, you're talking about ICT systems, automation devices, and the rest. Well, what are the challenges that we could face in the future as regards the inclusion of ICT in the power grid structure, in enabling and improving reliability? So what kind of challenges or problems can we face, and how do we plan to mitigate against such things?
Yes, well, challenges from a reliability perspective, well, there are various. One of them is of course, climate change, right? I'll give you a personal experience. I live in Houston, Texas, in the Gulf Coast, Gulf of Mexico coast here in the U.S. And we have hurricanes every year, right? They may not impact Houston specifically, but they impact the Gulf every year. The last few years, the frequency of those events and the severity of those events has increased, and analysis indicate that it's correlated with climate change. So that's one example, because when a good amount of the distribution grid is overhead, and even if it is underground, but if you have a major storm, a category 4 or 5 storm, distribution grids are not going to be designed to withstand those type of wind speeds. So the distribution grid is going to be damaged, right? And although generally to exclude those type of events from reliability calculations, the reality is that they end up affecting customers. So they affect the customer experience. And we have learned to some extent, we are kind of resigned to, we are kind of, I would say, we have accepted that reality, but that doesn't mean that reality is ideal. So we need to come up with new solutions to increase reliability and to increase resilience of the grid, so the grid can withstand or can recover quickly from those type of events. So that's one example. Another example is aging systems. So we need to realize that, especially in Europe and also in the U.S., some of the systems that provide service to important cities, they were built in some cases over 100 years ago. And some of those assets are still providing service, especially old underground systems. We have cable that is really aging, and eventually those assets are going to start failing, and we need to replace them. So aging systems, climate change are two key elements, and that relationship, a close relationship or increasingly close relationship between transmission and distribution, and the adoption of more and more inverter-based technologies, which that implies a reduction in inertia, right? The rotating inertia that we have used historically as one of the foundations for operating the grid So when that inertia starts decreasing, because we are going to adopt more and more inverter-based technologies, and more the distribution grid injects power into transmission, it's a new world, right? So we need to come up with new ways to operate the grid in a reliable way, and to plan the grid as well. So those are some of those challenges. And going back to analytics, of course, if you want to address those challenges, you need to process data, collect and process data. And the challenge there is that still today, I would say that we have a good amount of data, but we don't have, in my opinion, sufficient data. There are exceptions, but generally we don't have sufficient data to do some of these beautiful predictive and prescriptive analytics. In the future, we will. I would say probably in the next 10 years, we will have sufficient data. But then the challenge is going to be, we may have too much data, right? So how do we process it efficiently? How do we produce information that is valuable for system planners and operators? How can we avoid overwhelming them? So that's another challenge.
Yeah, I agree with you. Yeah, I think there'll be a lot of data, and the speed of and the processing power of systems in the generating outcomes for planning methodologies and the rest will be very key. And I think the question we have here right now is, from your wealth of experience, you talked about flexibility being a great option in modernizing the grid. Which area of the grid do you think we should concentrate more, or we should prioritize in terms of flexibility, generation, demand, or transmission?
Wow, that is a good question. I hadn't thought about it.
I mean, there's been rising calls for demand response, improving, I think, demand flexibility. Also, we're talking about modernization, inclusion of DEROs and the rest. So it's kind of a, I don't know.
Yeah, so I'll give you my answer. I must be honest, I hadn't thought about it, but I think that probably demand side flexibility, I think that is untapped. That's what I think it is happening. Power flexibility, I mean, there is clearly also a need there, but I think that we are addressing that with more and more with the deployment of energy storage, for instance.
Yeah.
Still, we need to do more, right? Because we need to do more in terms of long-term energy storage. I mean, we have the technologies that we have today are short-term or mid-term energy storage, but long-term energy storage is something that is key at bulk power system level. But I think that controllable demands, it's untapped. I think that there is plenty to do there, and we have energy efficiency, we have demand response, we have also storage, we have DER in general. There is plenty that can be done. Load control, there is plenty that can be done in that space.
Yeah, I agree with you. I think that's a wrap for now. Thank you, Dr. Julio, for your time, for coming around, for taking time to present. Okay, is there another question? Oh, good. Still have much time. We have like 10, 15 minutes more. Anish, with DERO, the generation has become unpredictable, hence the priority is to match the. Oh, okay, she's just the person is just reiterating what we've been discussing. So yes, thank you, Dr. Julio, for your time, for your presentation. We are sincerely very grateful. And so I'll be moving forward just to make some. Hello?
Thank you for it has been great. My pleasure.
Yeah, okay. Just moving forward, just to make some announcements. Like Dr. Julio said, data analytics will be very key, a key solution in modernizing the grid. And funny enough, our next DLP, which is going to be next month, 19th next month, is on the power of data analytics in electric utilities. This will be anchored by Dr. Siri Verandan. And so if you'd like to know more about how this can be, how this is applicable in electric utilities, and you want to go more, you want to know more in depth about this whole play, you could just scan the QR code here and register, so you get notification of when it's happening and when. And yeah, I think it should also be in the chat box. My colleagues will put it in the chat box, so you could click on the link and yeah, you could register easily. You could also, I discussed earlier about our feedback from the survey form. So I think the link should also be in the chat box right now. And so we'd like to get to know what your take on our program is and what you'd like us to improve on. And you could also follow us on our social media channels. We have a number of them there. Where you could easily just scan the QR code and go to our website. Then you see the links there. So you could just click and go straight to the social media channels. And any other addition, any other take on this? Yeah, on behalf of the IEEE PES Student Branch Committee, yeah, the University of Manchester, I would like to thank Dr. Julio for his time, for his presentation, and I would like to appreciate all of our attendees for coming around and learning more of this. The presentation has been recorded and will be uploaded to our website. And yeah, you could watch it and rewatch it. And if you have any question, you could send us an email that is on the screen right now, then we'll be able to communicate back to you. And once we get the slides from Dr. Julio, would, if you need it, we would send it by the Eventbrite registration. Thank you for coming around, and do take care. Bye for now.
Thank you so much. Have a good day.
Yeah. Bye. Have a